Welcome to this first week of the course Observation Theory, Estimating the Unknown. To get started right away, let's have a closer look at the title of the course. 3 keywords are important in the title. These are observation, so we're observing something or measuring something. Estimation, second one, which I will address in a minute. And the unknown, which refers to some kind of parameter that we are interested in. The relation between these two fields, that is the red arrow, needs to be established. It is what we call an estimation problem. So what is an estimation problem? Well, in this course, estimation has a specific meaning, which is different from the ordinary use of the word estimation. In ordinary life, we could easily estimate the number of walnuts in this image. If we have enough time to count them, everybody would probably come up with the same answer. So there would be practically no error. However, in the right image, if I would ask you to estimate the number of walnuts in the bowl, you would probably need to start guessing. Different people would arrive at different answers, and the likelihood to get the correct or the right answer would be very, very low. In fact, only by looking at this picture, there is no way to really know whether we found the right answer. So here, the measurement or observation is our visual perception of the picture with the walnuts, and the unknown parameter is the true but unknown number of walnuts. The relation between the observations and the unknowns can actually be viewed in 2 directions. If we would already know the correct answer for the parameters, and we know how they are related to the observations, we call this the forward problem. In most cases, this is very easy. If we know what the answer is, we can find a set of observations that matches perfectly. Our problem occurs in the other direction. We call this the inverse problem. How do we determine the unknown parameters given a particular set of observations? Since this inverse problem is notoriously difficult, we often cannot really determine or calculate the right answer. We have to engage in a process to get as close to the unknown parameters as possible. This is what we refer to as estimation. Now, let's get back to our video of the canal measurements. The 4 student groups were challenged to measure the width of the canal. Thus, the unknown parameter was the same for everyone. Ideally, the outcome should be a single number, equal for every team. However, each team came up with a different method to estimate this parameter. 2 teams, the upper ones, attempted to measure it directly, to swim to the other side and measure it with a rope, or to use a laser distance measurement to measure it electronically. The other 2 teams used indirect measurements. They measured a different distance at the side of the canal and aligned a triangle in a specific way, or they measured angles using a fancy instrument in combination with another distance. So, using a different set of parameters, of measurements, they tried to estimate the same unknown parameter. If we look at these 4 methods, which one would you prefer? Please take a couple of moments to think about it. You can press the pause button of the video now to interrupt it temporarily. Welcome back. And which choice did you make? What is the best way to measure the width of the canal? Perhaps when you were thinking about it, you first wanted to get some more information. What would be good questions to ask? Well, first of all, we need a criterion to know what we mean with the best way to measure the width of the canal. Best could refer to the cheapest way to find it, or maybe the fastest way or the safest way. In this course, we will define best usually as the method in which the precision of the estimated parameter is optimal. But maybe optimal is not even necessary. We don't need 10 decimal digits. Another question to ask is whether the students performed their measurement only once or whether they repeated it several times. Obviously, measuring it several times is preferable, since it reduces the risk of having an outlier. Moreover, we would be able to apply some kind of averaging to improve the quality of our estimation. It would also give us a way to say something about the reliability of the result. This is a concept which we'll discuss later. If we take a good look at these stills from the video, there is one more thing we should consider. Are the students really estimating the same unknown parameter? The width of the canal. What is the width of the canal? Where is it defined? The sides of the canal may not be parallel, and they even may not be straight lines. And how easy is it to determine where really the side of the canal is if you look at these two pictures? Determining whether we are really estimating the same parameter is a problem by itself. If both teams here would send you their results, they may both be very precise, but still be very different. In this course, we want to introduce a very systematic and conceptual approach in dealing with estimation problems. It involves a physical world and a mathematical world. And conceptually, when we deal with a real-life problem, we can always distinguish three stages here. In the first stage, our problem is defined in the real world, measuring the width of the canal. But we need to translate it to the mathematical world. In this mathematical world, we can apply all our tricks and methods to get optimal numbers as a result. We call this first step the linking of the mathematical model to the real world. In the last or third stage, we need to go in the other direction. The results from the procedures in the mathematical world need to be transferred back to reality, where we need to make decisions upon them. We call this the unlinking, or the disengagement of the mathematical model. In the canal video, we need to compare the numerical result with our knowledge of the real world. For example, if the width of the canal would be in the order of kilometers, something went obviously wrong. The stage in between, so the second stage, is the actual parameter estimation procedure, which takes place entirely within the abstraction of the mathematical model. Now, this conceptual framework is very important to keep in mind at all times, as both worlds cannot exist without each other. So to summarize, in this video, we introduced a number of important concepts: observations or measurements, unknowns or parameters, and the relation between these two, for which we engage in the linking and unlinking of a mathematical model. With estimation theory, we try to get an estimate which is as close as possible to the unknown parameter, where the optimality criterion is defined in terms of the precision of the estimated parameters.